This is Algebra 2, Unit 4, Lesson 3 on special factoring. A lot of this factoring you have had before. It is review. There are a few things that are a little bit new, and those things relate to things like factoring trinomials, things that you've seen before but maybe not quite in this way. So as we learn how to factor, there are a lot of different applications of that factoring that we can use. And so that's what we're going to concentrate on in this lesson. We're going to first review factoring trinomials to make sure you remember that before we go a little bit further. In a trinomial, the first thing you're always going to do is check to see if they have anything in common. If they don't, then you can go ahead and start factoring. If they do have something in common, you need to take out the GCA. In this case, 3x squared plus 4x minus 15, they don't have anything in common, so I'm just going to factor right off the bat. Now, I prefer that my students use the two sets of parentheses and just do the factoring mentally. You could also do the key form method or the key number method that we learned in Lesson 2, but that is a little bit more time consuming. So it is best if you can get this quickly because, you know, with those timed tests, you need to be the most efficient that you can. None of this stuff goes away. You're going to use it from now until you stop taking math courses. This stuff is going to be throughout all of those math courses that you take. So the first thing we're going to do is multiply 3 times 15, which is 45. And then we're looking for factors of 45 that subtract to give you 4. Well, if you think about factors of 45, we've got 1 and 45, 3 and 15, 5 and 9, and 5 and 9 do subtract to give you 4. So those are the two numbers that we're going to use. And then we have to consider factors of 3. Well, there are only two factors of 3, which make this one not too bad. 3x and 1x. 3 times 1 is 3. So we're going to use 3x and 1x. And then I'm going to ask myself, 3 times what gives me 9? Well, 3 times 3 gives me 9. So I'm going to put 3 there. That would be my outside term. And remember, your outside and your inside term, they would have to subtract to give you 4. So the outside term is 9. The inside term, well, 1 times what would give me the other term that I'm looking for, 5. So 1 times 5 would give me 5. And then to double check to make sure that your FOIL is going to work out, you always want to make sure that this last number times this last number is the last number in your original trinomial. Then the next thing we have to do is the signs. We know that this minus tells us that the signs in these are different. And if they're different, then one's going to be a plus, one's going to be a minus. And this plus here tells us that the big number needs to get the plus. The big number over here is the 9. So we need a positive 9 and a negative 5. So positive 9 means we would have a plus 3 and a minus 5 to get that negative 5. And we have factored the trinomial. You can always check it by doing FOIL. For this one, the first thing I'm going to do is take out a 2 because they do have a 2 in common. So I've got x squared minus 10x plus 25. This one is even easier than the first one was because there is no coefficient of the x term. So for this one, I keep the 2. Make sure you don't drop the number that comes out. That's extremely important, and that will be true through the entire chapter. So you could leave it like this. That was a perfect square, meaning we had 2 binomials that were exactly the same. And I could rewrite that 2 times x minus 5 if I'd like. The first special case factoring that we're going to talk about is factoring difference of squares. And when they ask you to factor anything, the directions are just going to say factor completely. And what you need to understand about that word completely is when you factor it once, you might not be finished. You might have to keep factoring to get it factored completely. You're going to factor until you can't factor any longer. You can't get it down any smaller than you already have it. And if we're going to factor completely, look at what we've got here. This is a binomial. Our middle term is missing. Normally when we do factoring, we have a trinomial or something with 4 terms if we're factoring by grouping. But in this one we only have 2 terms. So far, the only really thing that we can do with 2 terms is take out what they have in common. But if you notice, x squared and minus 81 or negative 81 have nothing in common. So this is one of your special cases. And the one thing you need to notice with this is each of these terms are squared. This is x squared, that's obvious, and then this one is the number 9 squared. Since there's a minus between those two, you have something called the difference of squares. And this is a really simple concept if you think about trinomials. Normally in a trinomial, like we had here, we had an x squared term, an x term, and then a term that is a constant with no variables, okay? Here, if you notice, the middle term is missing. Our x term is missing. So what this really means is we have x squared plus 0x minus 81. And this is always going to be the case when you have the difference of squares. When the middle term drops out, it was understood to be a 0. If you think about this like the trinomials that we've already done and we've already covered, didn't we say, okay, you multiply the coefficients, 1 times 81, well that's 81. What factors of 81 subtract to give you 0? Can't we still do that? Essentially, it's the same thing. That middle term was just gone. It wasn't there because it was understood to be a 0. So if you think about that, factors of 81 that subtract to give you 0, well, that's 9 and 9. So I'm going to factor this just like I've been factoring my other trinomials. Factors of 81 that subtract to give me 0 are 9 and 9. And then my signs, how I did signs in the trinomials before, is going to be the same thing here. If this is a minus, it tells me these signs are different. So that means one of them has to be a plus and one of them has to be a minus. And if you multiply those two things together, here's a vocabulary word we're going to learn later is conjugates. These two things are conjugates. And what happens with conjugates is the middle term drops out. When you multiply those two binomials together, your middle term drops out. You can do that real quick if you'd like. Do FOIL, and you can see that the middle terms are going to drop out. That will always happen in difference of squares. All right, so look at this one. We've got 3x squared minus 27. Just like with any other factoring problem, if they have anything in common, I have to take that number out first. So these both have a 3 in common. So I can bring out the 3. Then that leaves me with x squared minus 9. And look at what I have. I've got difference of squares. So instead of writing out that 0 term every single time I do one of these, that's going to be time consuming. If I recognize that it's difference of squares right off the bat, all I really need to do is do my 2 sets of parentheses, take the square root of the x squared, and put that in the front of each of those, take the square root of the 9, put that in the second term of each of those binomials, and I know that since this was a minus, they both have to have different signs. So one's going to be a plus, one's going to be a minus. So whenever you see difference of squares, that's what the factoring is going to look like. You take the square root of the first term, square root of the second term, those same 2 terms are in both of your binomials, and then they're going to have different signs. They're very simple. The trick with those is recognizing when you have them. And sometimes they like to embed those within more difficult factoring problems to see if you're actually going to factor it completely, to see if you're going to recognize how far you can go with your factoring. In order to get the right answer for these, you have to factor completely. Get all of the factoring that you can possibly done in the problem. All right, so looking at this one, we've got x squared minus 25. If I factor that, I recognize that is difference of squares. So I have x and x. Square root of 25 is 5, so I've got 5 and 5. One's a plus, one's a minus. In this one, looks like a 2 comes out. So if I bring out the 2, I have left an x squared minus 4. Keep the 2. Square root of x squared is x. Square root of 4 is 2. And one of them is going to be a plus. One of them is going to be a minus. So factoring difference of squares is really pretty simple. The big trick here is recognizing what you've got. Here is another difference of squares problem. I'm going to add another one here. If I give you something like 5x squared minus 20. See if you can do these two. Pause the video and try those two. Let's see if you can get the right answer. Okay, hopefully you've had time to do those. x squared minus 16 would give you x plus 4 times x minus 4. The order of those doesn't matter. You could put the x minus 4, then the x plus 4. That doesn't matter a bit. As long as you have both of those exact factors, you're fine. For 5x squared minus 20, I brought a 5 out first, and then I have 5 times x plus 2 times x minus 2. Now, I want to show you some examples of how they might embed difference of squares into a little bit more complicated problem. So I've got here a factoring by grouping problem, and we're going to do this one together and look at what we end up with to see if you recognize where the difference of square is. And we're going to talk about what it means to actually factor completely. We've kind of touched on that a little bit, where if we have a common factor in the whole thing, we bring the factor out and then we factor the rest of it again. That is an example of factoring completely because we've had to factor more than once. But this one takes it a step further. And as we go through this section, I'm going to show you several different examples of where we're going to take that a little bit further each time. So with this one, the first thing I noticed with that is it's got 4 terms. So I know I'm probably going to factor by grouping. Okay. The next thing I'm going to look for is I'm going to see if anything comes out of this whole thing, because if it does, I need to take the common factor out first. And I noticed that they all have C's. So I know I can bring out a C from every one of those terms. So I'm going to do that. If I bring out my C, I have left C cubed plus C squared minus C minus 1. Then the next thing I'm going to do is I'm going to try to group them, but I know with factoring by grouping, this has to be a plus if I'm going to factor by grouping. So I can't change the value of that, so I need to change that to a plus a negative, so that I'm making it look different, but I'm not changing its value. Once I've done that, then I can factor by grouping. I'm going to bring that C out and leave it over here to the left, because that is part of my answer, so I don't want to drop what they had in common at the beginning of the problem. So that will be part of my answer, so I'll just leave it here for now, and I'm going to work with the rest of the problem. We'll just pretend like that's not there for now, but I don't want to drop it, because when I drop something out of my work, I end up forgetting to put it back in at the end. So it's a good practice to leave it there, just ignore it until you get down to the end, and it'll be part of your answer. So if you look at this one, factoring by grouping, what we do is we take out the greatest common factor for each group. So with this, they both have a C squared. So I can bring out a C squared. When I do that, I have a C plus 1 left inside. On this one, remember that negative, whenever we put the negative in front of the second term, we always have to bring it back out when we factor. I don't see anything else that those two have in common, so my common factor here is just going to be a negative 1. So I'm going to bring out a negative 1 for that one, and I have a C plus 1 left. Now, hopefully you notice from this term and this term, they have a C plus 1 in common. So that's what I'm going to distribute out of these two terms. Now, this C comes down as part of my answer. I'm taking out the C plus 1. And then what's left in this term is a C squared. And in this term is a minus 1. Now, a lot of my students would look at that and say, I've factored by grouping, I'm finished. But what you have to recognize is, if you have difference of squares in your problem anywhere, you're not finished. It has not been factored completely, because this term right here, or this binomial, can be factored again. So I'm going to bring down my C, it's part of my answer. The C plus 1 is part of my answer, and then I'm going to factor this difference of squares. The square root of C squared is C. The square root of 1 is 1. One of them is a plus. One of them is a minus. Now it has been factored completely. Before we go any further with factoring completely, I want to make sure I review with you how exponents of variables work when you're dealing with simplifying them. When we multiplied monomials together in Algebra 1, if you multiply two monomials together, the rule is let me just show you where it comes from first. If I have x to the 5th, that means I have x written 5 times. So that x to the 5th means I have 5 x's. This x to the 5th also means I have 5 x's. So if I have these 5 x's times these 5 x's, don't I really have x to the 10th? And that led us to a rule that says if you have a common base to an exponent, and the exponents don't have to be the same for this to work, but if you have a common base, all you have to do to multiply those monomials together is keep the base and add the exponents. So essentially what that is x to the 5 plus 5, or x to the 10. How do we know that? Because of this. But nobody wants to write that down, that x down 10 times to solve that, okay? So we need shortcuts sometimes in math to keep us from having to do this kind of thing. And if you do enough of them, you see the pattern, and you know you can just memorize the rule. If the bases are the same, you keep the base and add the exponents, okay? So that leads me to a square root of an x, or the square root of a variable to a power. If we're taking the square root of something, doesn't that mean we're trying to find what multiplies by itself to give us the number inside? Okay, and what we could do here is we could write out x 16 times, and every 2 that we have, we can bring 1 out. But if you think about it, when you have an even number, well, wouldn't pairs be just the same thing as dividing it by 2? So if I take the root number and divide the exponent by that root number, I can get the square root very easily. So if I take 16 divided by my root of 2, I get x to the 8th. And if you think about that, if I take x to the 8th times x to the 8th, wouldn't that be x to the 16th? Because I keep the base and add the exponents. Okay, so that is some information that you really need to understand before we get into the more complex factoring. And you'll see why in just a second. In this one, that one is difference of squares. It's a little disguised, or a lot of students have trouble recognizing that. But in order for you to know that this is difference of squares, what you have to understand is anytime you have a variable to an even power, well, that even power, when divided by the root of 2, gives you another whole number, okay? So if I take the square root of x to the 16th, wouldn't x to the 16th be the same thing as x to the 8th times x to the 8th? So this is a square number. We're used to just seeing x squared, but as long as the exponent of that variable is even, it is a square variable, okay? This 1 still works the same way as any of the other whole numbers. 1 times itself, 1 times 1 is 1, so it is a square number. So if I'm going to factor this completely, remember that's what your directions will say, factor completely. So if you're going to factor this completely, what you're going to have to do is figure out what the square root of each term is. Well, the square root of x to the 16th is x to the 8th. So we've got x to the 8th and x to the 8th. The square root of 1 is 1. One's going to be a plus, the other's going to be a minus. We've solved that difference of square problem. But the directions say factor completely. Well, if we have factored once and we still have perfect squares in both terms, then it can be factored again as long as it has a subtraction. So what you're going to find with these is some of them cannot be factored more, but some of them can. Okay? So with this one, that one is still, both of those are square numbers, but it's not the difference of squares. So we have to keep that one x to the 8th plus 1, because remember, difference of squares only works if they're both squared and we have a subtraction. With this one, they are both squared and we do have subtraction. So what's the square root of x to the 8th? Hopefully you're saying that's x to the 4th. The square root of x to the 8th is x to the 4th. The square root of 1 is 1. One of these will be a plus, one of them will be a minus. So now we need to recognize, is this finished? Have we factored completely? Well, this is a sum. This is a sum. This one is a difference, so we need to check it. Is it the difference of squares? Well, yeah, that's an even power. So that's a square number, and 1 is a square number. So we can go a little bit further with this one. So that's x to the 8th plus 1, x to the 4th plus 1. Remember, these can't be done again because they're sums, not differences. This one, the square root of x to the 4th is x squared. The square root of 1 is 1. One of them will be a plus, one of them will be a minus. Then we need to look and see, can we go again? Or are we finished? Let's look at it. Well, this is the sum. Can't do anything else with it. That's a sum. Can't do anything else with it. That's a sum. Can't do anything else with it. That's the difference of squares again. So let's go a little bit further. These three just come down. We can't do anything else with those. This one, square root of x squared is x. Square root of 1 is 1. We've got 1 as a plus, 1 as a minus. We have factored that completely now. So sometimes it's not just as easy as factoring once. Sometimes we're going to have to keep factoring until we get to the end of the problem. Okay? So with this problem, if you only factor it once, you haven't even done half of the work. So if I were grading this problem and you got it to this point, but you didn't get it very far, if that were maybe worth 8 points, I'd probably give you 2 of them because you did about 1/4 of the work. Okay? So you have to recognize when you have a difference of squares. The directions again are factor completely. What we're going to do here is we're going to notice, hopefully, that both of those have a 2. They have a 2 in common. So I'm going to bring the 2 out first. If I do that, I've got x to the 8th minus 16. Then this is difference of squares. Remember, to get the square root of x to the 8th, you divide the 8 by 2. It would be x to the 4th and x to the 4th. I'm going to let you pause the video at this point, see if you can finish that one, and then we'll check our answer at the end. Hopefully, when you did that one, you recognized that the square root of x to the 8th is x to the 4th. The square root of 16 is 4. One of these is a plus, one of these is a minus. This can't be done anymore. Nothing else can come out of that one. But this one is still the difference of squares. So I have a 2. I've got x to the 4th plus 4. Square root of x to the 4th is x squared. The square root of 4 is 2. This one's a plus, and that one's a minus. That is as far as we can go with this one. Now, let me point out a common mistake. I see this a lot. Students will see this one, and they'll say, oh, that's difference of squares also, because 1 plus 1 is 2. You have to multiply the factors to get a square number, okay? So if you thought this was x plus 1, x minus 1, it's not, because 1 times 1 is 1, not 2, okay? That's a common mistake I see. So I like to show this one as an example to make sure we're not making that mistake, okay? So that one is factored completely now, and that's as far as we could go.